30 confidence intervals, all at 95% confidence. What's the chance they're all right? 0.95 times 0.95 times 0.95 to the 30th power. So you have to make adjustments for that. That's where hypothesis testing comes in. That's the beauty of it. That's where this idea of hypothesis testing comes from. Check out this. It's so easy to defend the status quo. We'll come back to that in a second. What that basically means is you have a belief that's commonly held, which is better known as the null hypothesis. We'll get into this more on Thursday. When the end don't justify the means, you run a study, crunch the numbers like we've been doing either with a confidence interval or with a hypothesis test. And the results you get are in opposition to what you were expecting to get. It's just that 180 degrees. We often use that phrase. We've gone 180 degrees, which means
we're turned around.
We've turned around. We believed this, now we believe that. No effects nailed it. Remember what I asked you earlier? It's still on the board? It might be. Hang on. No, I erased it for the exam review. I asked you earlier. Just for a second. I asked you earlier. We had a Colorado confidence interval for cardio techs. It's a lot of C's. It was from 45 minutes to 62 minutes. And I said, is the PA parameter of 35 minutes less? And you said, yes. What you go into is you start by looking at the Colorado confidence interval. That's your status quo, if you will. The PA is nowhere near the interval. So you're expecting it to be in the interval. It's not. Therefore, you have to say, no, it's less. They're not the same as Colorado. They're different. Now, this is not the easiest thing to understand. So this is the one geometric example I want to do with you guys today. That's it. One geometric example. You can just sit back and take this in. This is you won't be required to do geometry in this class, for goodness sake. But I do think it's going to make it sense. A proof by contradiction is the order of the day. I want to tell you a story about my high school years. I tried to throw discus in high school. Tried. They built it, well, I'll tell you about that later. So it was on 18th and Broom Street was my high school. 18th, was it Broom or 18th? It doesn't matter. One of the streets was right next to the practice field for track. It's here. And I would stand there and I'd throw my discus. And anybody throw discus in high school? Come look, a whole bunch of you. That's awesome. That's awesome.
Junior high.
In junior high, but you've thrown it. You know the process. So, you line up backwards, and then you start to spin this way, right? Spin this way, spin this way. Whoa! And then you want the thing to go that way. So when I was learning how to throw a discus, I wanted to go that way. I let it go here. Well, the problem with letting a discus go here is that it goes that way. So I was putting car windows out and house windows out. I went back to visit my high school about 5 weeks, 6 weeks ago. There's a big cage around the discus circle now, which I'm pretty sure is the Sean Rule Memorial Cage. So what I want to do is, I want to prove for you, mathematically, that when you have a circle and a point escapes the circle, it escapes at a right angle. I call it the Discus Theorem because I'm reminded to my high school days. So I'm going to slide this guy over here. Now, again, this is called a proof by contradiction, and you're about to see the point of a proof by contradiction, okay? So here's what we're going to do. And again, this is pure geometry. You are not responsible for geometry in this course. But you will be responsible starting on Thursday afternoon or Thursday at the end of class, after we finish the exam, to this kind of thinking, which we will develop over the course of the next 6 weeks together. So here's an overview of it. So the geometry, not so much, but the process and the logic. Here's the deal. This is the circle Sean spins in. Pretend it's a circle, not like a pair. That's a circle that Sean spins in. So here's Sean in the middle. We'll call that point S. And here's Sean's hand out here. We'll call that point H. This is Sean's arm. When Sean lets go of the discus as he's spinning, it doesn't matter which way he's spinning. All that depends on which direction the discus heads. The direction the discus heads is governed by the angle that's formed between S and H in this line. So what I'm going to do is I'm going to call this line line D for discus. So mathematically, what I want to do is I want to prove to you why I kept breaking windows, other than the fact that I was. So in geometry, how many of you guys remember doing this in geometry? Prove that SH, which is a radius, prove that radius SH is perpendicular, which we call with a little funny symbol like that, to line D. Remember doing proofs in geometry? Some of you, a couple of you. Anybody?
Remember geometry?
Maybe. Well, you're about to remember a little bit of it. So here's what we're going to do. We're going to prove that if this line right here, which is called a tangent line, and again, there's a lot of terms from geometry class you don't have to remember except for right now. This is called a tangent line to a circle. Remember what a tangent line to a circle is? Think about a bike chain. Think about a bike chain. When the chain comes into the gear, if the chain kept going and didn't wrap around the gear, it would hit the top of the gear and then just keep going. A tangent line is a line that hits a curve in one point and then keeps going. As opposed to, I think, like a diameter, which hits it across the circle in more than one point. So all a tangent line is, it basically kisses the curve and keeps going. So if you think about it, that's when I let go of the discus. It's already in circular motion. I let go of it and it escapes the circle. It was touching it at one point and now it's gone. So that's what a tangent line is. I gotta prove that it escapes at a right angle. How the hell am I going to do that? It's extraordinarily challenging. So what you do is, you do what's called a proof by contradiction, and you start by assuming. Assume it's not perpendicular. You assume it's not perpendicular. Guess what we're going to do to that statement? We're going to prove that statement wrong. If we can prove that statement's wrong, then that one has to be right. Work with me here. One of two things is true. Either that line is perpendicular to that, or it's not. If we can show it's not perpendicular, it's not perpendicular, that means it has to be. Yes. Double negatives are okay. Totally fine. Mathematically especially. If we can show this doesn't make sense, then this has to make sense. So, let's do it. Now there's...
You can only do that when there's two outcomes.
Yes, but you can always make two outcomes. Show something's equal to 40 degrees, assume it's not. Show something has increased, suppose it hasn't. You can always make something binomial. This goes back to 243. You can always make an argument binomial. You might lose some refinement in doing that, but you can always make something binomial. Yeah, but and these are the two outcomes. Yes and no. Now there's something you have to remember from geometry. I'm sure you've forgotten. And this is the deal. We've got a point up here, point S. And we've got a line down here, line D. At some point, I have to be able to drop a line from S and hit line D at a right angle. I have to be able to do that. There's a postulate in geometry that says that. What we just assumed was, it's not SH. So it has to be somewhere else. So I'm going to put it over here. ST. So, since SH is not perpendicular, some other line has to be. So I'm going to assume that ST is perpendicular to line D. Okay? So now, to make you believe it, I'm going to put a little right angle marker on it. There. Now it has to be. Now it has to be. Because I put a little angle marker on it. Yeah. Now you can't argue with me. No, I want you to argue with me. I want you to prove to me why that doesn't make any sense. I want you to prove to me why that generates what's called a contradiction. A contradiction is a mathematical fallacy. It's a mathematical butting of heads. Why can that picture not exist that I just drew? That picture is impossible. Walk me through a series of mathematical steps. Ashley, help me.
Well...
Oh, I'm going to give a point here. Point A for Ashley. That will also help us. That will also help us. Point A for Ashley. Go ahead.
You can't just draw a line there and say it's perpendicular.
But there has to be a line somewhere that is.
Yeah. But
And if it's not that one, it's got to be some other one.
I don't think they're both perpendicular.
Oh, they can't be. The only way they're both if they're parallel, they both be perpendicular.
That's what I was going to say.
So this one, this one's not it.
One of those is not perpendicular.
So prove to me why it can't be this one. Go ahead, Michael. I love what you're saying, Ashley. You're right.
Because where you're releasing it is outside of your circle.
Okay, so what does that mean, Michael?
Well, that means it's outside of your reach. You've released outside of your reach and somehow it's...
Oh, no, careful, careful, careful. Forget the discus introduction for right now.
Okay.
I'm just saying, why can't this figure exist? I've made the right angle be on line ST. Because we're assuming it's not on line SH. Please, Spence.
Well, assuming it's a perfect circle, SH equals SA.
Okay,
So-
stop right there. That's perfect. Hold that thought, Spence. You hear what he just said? If this is truly a circle, that means SH and SA have to be the same because they're both what, Spencer?
The radius.
They're both the radii of the circle, so they have to be uniformly congruent. Keep going, Spencer.
So for AT to be a right angle, AT would have to be 0.
Okay, why?
Tangent line doesn't intersect.
Say that again.
Tangent line doesn't intersect the arc. That tangent line doesn't intersect the arc at point.
Sure, but that's the definition of a tangent line. Why does it make, why does this, why are we've created an impossible situation. What, let me give you a hint. What kind of triangle have I drawn? By dropping in ST? Oh, and look, it's partial. This is isosceles right here. What kind of triangle is this? Since it has a right angle. I just gave you the answer, actually. It's a right triangle.
Right.
Sorry. Damn it, give you the answer. Hang tight. Hold that thought, Bob. I want to hear from you. I want to extract this triangle out, okay? S, H, T. Here's A. We've already decided that SH and SA are the same length. And I'm telling you there's a right angle right here. Bob, give me your thoughts.
Yeah.
Negative? Negative, that doesn't make sense. Good. Mathematically, Lindsay?
So, if you were to draw the line from H to A,
Yes?
then it wouldn't be a right triangle because it wouldn't add up to 180 degrees.
Well, you're assuming that's already 90. I think.
Yeah, but you're not, but your triangle of, never mind.
No. You're onto something, friends. You're onto something, Lindsay. Check this out, friends. You ready? Assuming that's a right triangle. Let's go back to assuming this is actually a correct figure. What's the longest side in this triangle? If it's a right triangle. If it's a right triangle, what's the longest side? SH has to be. Forget A for a second. Since the right angle is here, this is like, Lindsay, you're hitting the right idea. Since this is 90, this is the biggest angle in the triangle. Which means the biggest side has to be opposite the biggest angle. Which means, by geometry, SH has to be longer than ST. I mean, that's what geometry tells us. In a triangle, bigger sides opposite bigger angles. As the angles open, the sides that are opposite them get longer. But ST is made up of SA and AT put together, right? And Spencer just told me that SH and SA are the same length. So I can kind of cancel those off the inequality, if you will. And we just showed that this is true. We just showed that the length of AT, which is that little extra bit outside the circle, Michael, you said I'm not letting go outside the circle. Well, what did we just show about that length of AT?
It's outside the circle.
It's less than 0, which means the length of that segment is negative, which is what we call we just got a contradiction. So let's now check this out. This right here is a contradiction. What we now have to do is backtrack to see where we made the first wrong assumption. That's a contradiction. But that came from this statement here. Well, this statement is perfectly logically followed by this one, so that one's okay. This statement, perfectly logically followed by this one, so that one's okay. This statement, perfectly logically followed by this diagram, so the diagram's okay. Susie?
Would it be your D line is an error?
No, the D line is, we define that to be a tangent line. That's fine. Where did all of this argument come from, friends? When we assumed that SH wasn't perpendicular. Every argument after that was based off of that assumption. Which means we did a bunch of really good mathematics. That was all based off of an erroneous assumption. What does that mean about this assumption right here? That means that assumption is wrong. So in other words, we assumed that SH is not perpendicular. And we showed that with that assumption, we get a contradiction. Now, I love what Ashley was saying. I chose to put ST over here. Suppose I chose to put it over here instead. Would I get any different results? No, the exact same argument. The exact same argument. As a matter of fact, anywhere I put ST would yield the exact same argument, except if I put ST right on top of SH. Ooh, SH is over here, excuse me. So, if this is untrue, we just proved that ST can't not be true. What does that mean about SH? It has to be this, excuse me, I said the wrong thing. We just showed that SH can't not be perpendicular. That means SH has to be perpendicular. That's the way you do hypothesis testing in this class. You start by assuming the opposite of what you want to prove, and you get to where you actually do want to prove with 95% confidence. No geometry involved. No geometry involved. But that's a perfect example of how the logic and process behind it. More on that on Thursday after your exam. More on that on Thursday after your exam. I got a whole bunch of articles for that. We'll see. No. You'll see.
I'm worried about that.
Why are you worried about that? It's not on your exam.